So, now that we kind of recognize where big data fits in to our particular needs, we have to realize that we've kind of come to the end of the line for a lot of these technologies that we've been used to and we've been working with for the last 20 or 30 years. We actually have physical limitations on our online transactional and online analysis processing systems. When you look at it, we also have the idea that we've got massive amounts of data, and a lot of us have been putting this data on tapes, and then the tapes are going into some sort of a climate-controlled warehouse. If any of you out there have ever set up a storage area network, and I had one experience of doing it for my household, you realize, number one, it's quite expensive. Initially, I went to eBay, I got my enclosure, and then I'm an engineer, so what I do is typically I don't read documentation. I went out and bought 42 terabyte Western Digital drives on eBay and then proceeded to put them in the enclosure and then found out nothing worked. I read the documentation, found out that storage area networks require very specialized hard drives that are typically quite expensive. So for a storage area network, we have both the expense and we've got the fact that it's not for an amateur to set up. So we've got to have a place to just be able to put our data. And then finally, another one, what we bring to the picture when we're looking at big data is we actually give you a supercomputer. However, you're not paying millions of dollars. You're not having to use very specialized operating systems and very specialized programs that have been written to take advantage of the parallel processing and the pooled RAM. All of that comes when we're working with many of these big data systems. So we're able to once again overcome the limitations of our traditional database processing. We're able to get a storage area network for pennies instead of dollars, and we're able to have a supercomputer capability that we can easily scale and extend out. So that brings us to this whole idea that if you have worked with a storage area network, it's not the easiest thing to scale it up. We have to buy more enclosures, we have to get more of the hard drives, the specialized hard drives, and then of course we have to make this entire system work together. For a supercomputer, it becomes even more difficult to be able to scale this thing up or out. So when we're working with big data, if I need either more processing capability or I need more storage, it's a simple matter of getting another box, putting more RAM, more cores on the system, and putting more drives on the boxes. So it's a very, very easy proposition. And because we're using commodity hardware, we don't have to go out of our way to get the most expensive machines and the most expensive components that are available out there. We also have to realize that the hard drives we're using, unless we're using some of the brand new ones and the flash drives, these are the same hard drive architectures that we were using 30 years ago in the mainframe environment. So things have not changed. We still have to manipulate a physical read-write head across a platter, and we still have to pick up the blocks that have been striped down upon the platter. So Hadoop takes advantage of this old architecture by not allowing us to do random seeks on the hard drive. The information instead is put in fairly large block sizes, and the read-write head is positioned at the beginning of these blocks and simply scans all the way through to the end of the block. So it's actually able to leverage these technologies as best we can. And then finally, if you're a programmer and you have done threaded coding, you know that threading becomes almost an art form in whatever coding paradigm that you're going to use. We're going to get the advantage of parallel processing without having to do any threading code at all. All of this has already been built into the framework, whether it's on the side where we're reading the data, the mapping portion, or the side where we're pulling together our final results, the threading portion inside of the reducer. We don't have to do any threading code whatsoever. We're just simply taking advantage of what the frameworks are giving us. So to go back again to these older technologies, transactional and analytic processing, we actually have physical file limitations. Now, when you look at it, some of the specs out there say that physical limitation is 276 terabyte for one of these files. If you're working with fairly large data, though, in your transactional or your analytic system, you'll find when you start getting to about 4 or 6 terabytes, you are not at a physical limitation. You are actually at a processing limitation. And what's going to happen is you might be running a query, and not only will it not be real time, it's not going to take place in the milliseconds. Many of these queries on terabytes of data, and we don't even want to talk about what happens if you get into petabytes. But many of these queries will actually run over several days. If you can deal with that in your organization, that's a wonderful thing. But most of us would like our queries to be in the seconds or in the minutes, somewhere within there. So even if we haven't hit a physical limitation on the file size, we've hit a limitation on the actual processing, on how long it's going to take to query the data. We also have a situation now where the data is coming in so fast to us. And because of the intrinsic nature of transaction and analytic processing systems, it's all about schemas. We have extremely rigid schemas that we have to work with. So if the data is not going to fit into our system, we're going to have to do all kinds of ELT operations to prepare the data so that we can be doing our insert operations. So in this age when we're analyzing social media, we're analyzing machine sensory data, the idea of being limited to these very rigid schemas becomes counterproductive for working with analyzing this data. So we have to have some sort of a structure that is not quite so rigid within there. And then, of course, we have to scale these machines up and not out. The machines, the operating systems have to be very robust. The machines have to be fairly expensive, very reliable machines. And then, of course, our licensing expense is going to be climbing each time we scale these machines further upward. So that becomes a very limiting factor when we're looking at working with larger and larger pieces of data and data that's coming to us in faster and faster speeds. Once again, a lot of people are using big data. They're using systems like Hadoop simply as a storage area network. A typical storage area network I heard last week was going for $19 per month per gigabyte. That's quite a bit of money. And also the maintenance. These are not intuitively friendly systems if any of you have worked with them. So we've got those expenses and those maintenance issues. Then we start dealing with RAID, that we want to have our data striped out so that we have fault tolerance. If a hard drive goes out, that we've got a way to be able to still recreate the data. That brings up more expenses. That brings up more resources that we have to use. And it also brings up more inefficiencies in the actual storage itself. We have the idea of backing up. So normally we've got our network administrators that are backing up our storage systems, backing up our databases, backing up our personal files. And like I said with the RAID, we always have this idea of fault tolerance. The most crucial part of a system is going to be the hard drive. The hard drive is spinning at very fast speeds. 5200 for the less expensive hard drives, 7200 RPMs and higher. We also have a very fragile read-write head that has to be moving across the platter to pull up the information. So if one of these drives kicks out, a very big part of our plan is the idea of introducing fault tolerance, that this information has to be in other places. So once again, when we're dealing with big data systems, when we're dealing with things like Hadoop, a part of the built-in structure of this is a built-in fault tolerance. In the instance of Hadoop, a basic feature is that our data is maintained in 3 places at any given time. If a machine goes out, if a platter goes out, the machine responsible for the cluster, the overall performance of the big data cluster, is going to recognize that it only has 2 copies now, and it will give instructions that the data needs to be copied 1 more time. So we don't have to worry about fault tolerance, and we typically don't have to worry about backup mechanisms. The idea of big data as a supercomputer, so it's not just about the storage capabilities, though there's a lot of organizations out there that are using big data, they're using Hadoop, other systems, strictly as storage facilities. But what you also get is you get a supercomputer. If I have 100 machines and I have 4 CPUs on each machine, and each CPU has got 8 cores, I have 3,200 cores that will act in parallel together. Plus I have the pooled RAM for all of the different machines. So under anybody's definition, that really is the definition of a supercomputer. The pooled resources, both for the cores and for the RAM. However, I don't have to have a specialized operating system, which supercomputers are all about, and I also don't have to have specialized programs that have been written for this particular platform. I can just use things off the shelf, or I can have my programming teams make up things together that are really within their capabilities. So we've got this idea that the cores are going to be utilized very easily through here. In the new version of some of the big data systems, we now have a resource manager that is actually taking a load reading on all the machines across the cluster, across the network. And what it will do is it will get the highest core and RAM utilization that's possible. So it will notice if a machine is not up to its full capability, and it will simply assign more tasks to that particular machine. Like I said, we have the failover built into the system because by default we are keeping the information in 3 different places. So when I initially put the data down, the blocks are going to be copied to one of the machines. They'll communicate back with the master machine. The master machine will say, I need 2 more copies. I want you to copy that block onto this rack and onto this IP address. The machine copies it. That machine will then communicate with the master machine. The master machine will say, I need 1 more copy. Please copy it onto this IP address. So again, it's not up to the master machine to actually do the work. It's simply overseeing the process and making sure that it's got 3 copies at any given moment. So if a machine does go out, we have 2 other copies, and the master machine at that point will contact one of the data machines, the data nodes, and instruct it to start copying the blocks onto another machine so that once again we're at our 3 copies. And then of course the expense. The expense on this is commodity hardware. Now this doesn't mean going in your closets and pulling out old machines that nobody has touched for the last 10 years, but what it does mean is that I can go to a vendor and I can get very basic machines. They don't have to be the most expensive machines. We can still have that for processes that we rely on, our databases. the master processes within our cluster, but the basic data machines can just be very simple servers. The operating systems that they can support Windows 2008 R2, 2012. Most of the systems out there are using some form of Unix, and typically Linux. So for a lot of us, the expense is only the machine because the operating system is free. It's open source. So the expenses are very, very low. And then scalability. So initially, I say that I've got 20 terabytes of data that I want to be accountable for. That's the amount of information in my cluster. Now in reality, because of the failover, I need to have space for 60 terabytes, and most of the white papers tell you that you should have space for 80 terabytes for some scratch area, temporary areas. If I need more storage, if I need more processing power, more CPUs, more RAM, what I do is I put more boxes along my network, my cluster. It's very easy to set up. It's very easy to scale the system out. So running out of space, running out of processing capability should never be an issue within here. Again, in a normal system, in a storage area network, in a supercomputer, it is extremely expensive to scale up. Also, when we look at our database systems, whether they're transactional or whether they're analytic, when we scale up, we're going to be encountering a lot of expenses. We're going to be encountering the expenses for the machinery. We're going to be encountering the expenses for the licensing. So this is fairly easy to scale out. We scale it out horizontally. So instead of piling technologies upon each other and building this thing up and coming up with more and more expensive machines, we simply have more machines that we scale out horizontally. I want to put 2 more boxes on. I need more hard disk space. I need more cores, more RAM. It's very easy to scale this thing out. Again, more disks. I can also go into the machines that I have. If there's capabilities, if there's more open slots, I can put more disks in there. If there's more space available on the motherboards, I can always go in and put more CPUs, more cores, and more RAM. But if I've exceeded the capability of the boxes, I can simply get more commodity boxes, and I can add the capabilities that way. So the key term here is commodity hardware. We don't have to go out and buy extremely expensive, reliable machines. The way the frameworks are set up are we expect there to be failures. And the expectation is built into the system itself. So we don't have to worry about it. The main thing that we have to worry about is getting an operating system that we can depend on. And then, of course, as I mentioned earlier, we don't worry about writing code with threading. The parallelism is built into the system from the start, both on the reading end and on the writing end. So we just have to take advantage of it, and that's going to come in to how we place these blocks of data across our system. Now, I said earlier that the hard drives have not changed their basic design really since the late 70s, the early 80s. We still have a platter. The platter is spinning at some ridiculous speed. We still have a little metal arm that we have to manipulate around the platter to be able to get our data. Now, in most systems, that arm is moving all over the platter, which is extremely inefficient and also causes a lot of wear and tear on the machinery itself. So we've got this read-write head, and a lot of the issues occur with these seek operations, that we have a file. The file becomes fragmented as we evolve, as we append, delete, move, do other things. And so what happens is we start hearing the read-write head skittering across the platter. And it's involved in these random seek operations. So a part of what we do within here is we have a fairly large block system. So let's say I've got a 1 terabyte file. What I have to do is I have to instruct it on how to distribute out the pieces, how big to make the blocks. Maybe I want to make my blocks 256 megs. Maybe I want to make them 512. Maybe I want to make them 1 meg. But let's take an easy one. Let's say that I've got 1 gig blocks and then I've got a 1 terabyte file. So what that means is I have 1,000 blocks that this file will be split up into when it goes into my system. Now we do not support, the file system is an immutable file system, so that means once a block is written it cannot be changed. It can only be deleted. Also, we don't support random seeks. So what we do is we position the read-write head at the beginning of the block and simply scan all the way through to the end. So these blocks provide two things. The blocks provide a way of sharding out the data. The blocks also provide the parallelism on our reading operations. So if I have 1,000 blocks, I will probably have 1,000 parallel read operations that file is capable of supporting. And because I'm not moving the read-write head around in these random seeks, I get the most efficient work with its capability. I'm just simply scanning blocks from beginning to end. And then, of course, we have the built-in redundancy because we've got the blocks that are stored in 3 different locations. Also, we're working with checksums on both the files and the individual blocks, so each block and each file is constantly being checked to make sure that it's in proper order. If there's corruption, what will happen is the master device will ask for the files to be redone, and it will redo the block structure. The parallelism, we don't have to write the threaded code. The parallelism on the map side is dictated by the blocks. Once again, if I have 1,000 blocks, I have 1,000 read operations that can be supported in parallel. On the reduced side, the parallelism is dictated by the technology that I'm using. Typically, the programmer or the business analyst will go in and say, I want 70 reducers. I want 110 reducers. So they'll actually go in and dictate the rules for the parallelism on that side of the operation. We also are going to have hundreds or thousands of jobs that are going to be executing at the same moment. So we have a resource manager that's responsible for keeping track of the load on each of the individual machines and making sure that the load is distributed fairly evenly and scheduling the jobs out using one of its 2 scheduling mechanisms. Now, as far as the scheduling goes, we can schedule the jobs in a variety of ways. There's several systems that are built in that will allow us to deal with workflows, and the workflows can typically be scheduled either as cron jobs based upon time. I want this thing run every Tuesday morning at 10 a.m. Pacific time. I want this thing run once a week. At this particular moment, I want it run once a quarter on this day. The other way I can schedule things is I can say, you know what? I don't know. My data is coming in from another group. It's coming in from a partner organization, another department, another division, and what I want to do is I want to find out and constantly check to see if that data has arrived in my system. The minute the data arrives in my system, I want to fire up my workflow. So I've got a variety of ways that I can automate and I can schedule these pieces out. Now, one of the things I constantly hear, we don't need big data. Our database is only 2 terabytes in size or 4 terabytes in size. So big data is not necessarily an answer for me. Well, you have to realize that, okay, maybe that's your data, but maybe I've got partners that have data and I want to integrate it in. Maybe I've got data that's available in open source. 3 weeks ago, I was at a client that deals with robotics, and they have manufacturing facilities across the world. And I showed them a website that actually keeps track of political instabilities across the world. And they have a database, or they've got files that can be downloaded every single night. And what they can do is literally every day they can get a report on where there are possible places for political unrest in the world. And this was very important for them because they've got factories in all these different places. So now this has become a part of their Monday morning meetings when they discuss that there could be trouble occurring in a part of the world where one of their factories is. This was something they didn't even conceive of before. We've also got information available from the government. Maybe I want to go to the National Weather Service. Maybe I want to go to the Department of Interior. Who knows? And that data could be available to me. Maybe I need to look at weather patterns, and I need to integrate that in with some of our planning. Social media. A lot of us were going in and we're sending surveys out to some of our clients, and we're trying to get feedback. The best feedback out there is coming from information that's on Facebook or information that's on Twitter. Again, it's massive amounts of information, so we have to have the means, number one, of pulling it into our system, and number two, of being able to analyze it, what's there. You know, maybe I just did an ad campaign and something in there was not working the way that I thought. Do I have to wait 2 or 3 weeks before I get my information back, or can I get instant feedback? So the social media, again, becomes something that's outside of our data, but it's something that we might want to integrate in. And then, if we're working with sensors, machinery, where information is flowing in, manufacturers of aircraft engines, jet engines, they generate 1 terabyte of data per engine per hour. That's a lot of data. If any of you have fairly recent cars, when you go into the dealership, a lot of those cars, when you do their tune-ups or when you do oil changes, what they'll do is they will actually pull the sensor data from your car and send it in to the manufacturer. And then they use that to make sure that their machinery, their hardware, is actually working within specs. At that point, you may get a firmware revision or something else going on. If you're driving a car and you've got a black box from an insurance company so that you're able to get a reduction on your insurance rates, they're working with massive amounts of sensor data. If you are going to look at having a driverless car in the next few years, again, sensor data becomes very crucial for all these things. So you can't just look at your system, your web logs, your machine logs, your databases, your analytics systems, your data warehouses, and say this is the only data that I'm concerned about. Because there's a lot of data out there that could be of extreme use in your organization. So that brings up the idea that maybe our competitors are using this data. If they're using it and we're not, then we're not going to be able to compete on their level. So we want to be able to get an edge on this thing. Once again, what does the public feel about your services, about your products? There's a place that measures TV audiences and what they like, and their surveys are used to price advertisements on the various TV shows. And if you look in the paper, you'll see that they publish their results out once a week. Well, what they do is they rely on a box for just about a little over 5,200 families, and then they use that to kind of set up what American families are watching, and then adjust the prices of advertisement according to that. If you go on Twitter or you go on Facebook, you will know instantly if a new show's come out, or if a season finale's come out, or if a show's gone in another direction. You'll be able to know instantly what the people feel. Do they like it? Do they hate it? Do they have other comments? And that's data that's freely available to us. So again, it's being proactive. What do our customers feel? What else can we offer for our customers that will expand out our services and our product line? And then there are the people out there, the math wizards. And the math wizards are going in here and they're looking for patterns. The bigger the data, the better it is for those folks. So these are people that typically have masters or PhDs in statistics and probability. To give you an example, a very, 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 very large retail chain was sifting through their data and their weather patterns. And what they noticed was before a huge weather event, let's say a hurricane, a blizzard, something else, they found that people were going in their stores, flocking into their stores, and buying, of all things, Pop-Tarts. And I was amazed. I was actually talking with one of the people that works there, and they said, yep, 6 of us discovered this, and it was Pop-Tarts. So what we do is we monitor the weather, or someone monitors the weather. We have special people in our stores that about 11 o'clock at night, when the traffic's died down somewhat, they start moving things around. So what we do is we move the Pop-Tarts next to items that, let us say, are not moving as rapidly as we'd like. So these people are finding hidden patterns, hidden gems. A lot of this also has to do with security. Many of the security attacks now, they require a lot of planning. They're not just done instantly. So these people are setting things up on our networks, and then our data scientists are looking for these hidden patterns and trying to identify them. So this all is taking place as far as what direction are we moving in? Are we moving with the flow? Are we growing? Or are we going the other direction? And is our business atrophying? So in order to be competitive, in order to be relevant, we have to keep up with the amount of data out there and be able to analyze this data and see if we're moving in the right direction. So we come full circle to, okay, I understand the need for this. I understand where it fits in. What exactly is it? It's variety. So for variety, think about this. I would like to do a join on our email system, on stuff coming out from our data warehouse, on a table in our database, on things coming in from sensor data from our building, and also on the web log files. Now think about that. You can't do that very easily in your database system, but in big data, you can. So I can have all of these different pieces, these varieties of data, and be able to tie them together. Also, the fact is this data is coming at a fire hose speed. The minute we think we have a grasp on it, more data is flowing. And of course, the volume of the data. So it becomes a matter of leveraging this data, getting it stored, figuring out how to analyze it, and getting the most return on our time and money. So we have to look at this thing. Once again, maybe I've got 4 terabytes of data. Maybe my various partners have 8 terabytes between them, and I want to be able to integrate it together. And then maybe there's data being provided by other non-government organizations, by the government, by open source areas, and I want to be able to also integrate that data in. So all of a sudden my 4 terabytes is expanded out to 20 or 30 terabytes. So what we do is the common practice out there is, first of all, let's put it in the lake. Let's put it in the data store. Let's put it in the distributed file system, and we just keep dumping it in. Eventually, we'll deal with it, we'll analyze it, but obviously the first thing is to get it in the lake. So we've got all of this different types of data out there. There's all kinds of data in all of our organizations. We've got our traditional databases. We have our warehouses. We have many, many, many spreadsheets. We may have comma-separated files that are coming in from all over the place. They may be coming in from accounting systems, from customer management systems. Some of them also have mainframes that are out there. And we want to possibly have mainframe dumps. We've got files that are being scanned in, and we're looking at optical character recognition. Many of us want to have photos in there. Facebook's a great example of working with photos. But also, if you're in law enforcement, they may have photos of fingerprints, of faces for facial recognition. We also may be dealing with videos. We have log files everywhere. Web servers, application servers. We may want to analyze those for our performance and also for auditing and security. And the list just keeps on going. So there's a lot of data out there in different formats that we've never been able to consolidate. And it keeps coming. So what we need to do is become very proficient to get it in the system and to have these processes set up in an automated sort of way. So we've got our data, and then there's also data that we've been putting on tape, on disk. We've been putting them in warehouses. Some people may not have seen these things in years. Is it of any value? Here's an interesting use case. There was a Department of Defense contractor, and their claim to fame was that they had only had 7 intrusions in any given 6-month period. And that's pretty good. Well, they started working with big data. They started putting data in the system that had no use. There was no place to put it. So they started dumping all of this data into the system. What they discovered was that they were intruded over 500,000 times in a 6-month period. Now, whether that's a good thing to discover or not, it still is the truth. And they wouldn't have known it if they hadn't had this massive amount of data that they were able to pull up, put into their system, and start analyzing. So it also gets back to the fact that the more data we have, the more we're able to apply statistical and probabilistic patterns out there, and we can discover things that we may not have been aware of. And then we can start working on those patterns. So a lot of this is dependent on how much information is out there, how much we can put in the system. And then, of course, what are we missing? You know, there's always more things to be discovered, more things that we might be able to utilize and put in the system. So, you know, we've got our basic comfort zone. We want to keep our competitive edge. We want to do at least what the people we're competing against are doing, and hopefully do a little bit more. Be able to keep providing our customers with better services, with better products, with things to kind of talk about Steve Jobs from Apple, things that they don't even know exist. They don't even know that they need it yet. Who would have thought an iPod would become so central to many of us? And there was nothing out there that was even filling that gap. Most people didn't realize that the gap was there. So we want to go in here, we want to constantly be adjusting our models. We want to look at information that previously we might have archived, and we want to constantly be evolving. And then what about things that are changing, you know, political instability, weather, traffic patterns? There's people that are actually using big data to analyze traffic patterns. And a good example of this is Los Angeles County. They've actually been getting much, much better with their predictions and adjusting lanes on their freeways based upon working with big data and working with weather and working with events that are occurring locally. So all of these things are integrated in to give them an up on being able to predict the traffic patterns and being able to adjust the lanes accordingly. So we've got this massive amount of data. We want to get it in one place. I didn't realize it, but Google Translate what they do is they have massive amounts of data, and they're not using programming to figure out how to translate, let's say, from German to English. They're looking at data and they're looking at correlations. So the more data they have, the better able they are to actually predict that this particular sentence makes complete sense now in another language. So it's this big data. So we want to gather it, get it in a common area, and start analyzing this thing. So first things first, get it all in the lake. Get it in a common repository.